People seem to think products are just hatched, you know, they just shoot out of the factory. Somebody just pushed a button and there it was. The amazing thing to me is that people don't know of the industrial design profession, but they're affected by it constantly. The way it looks, the way it feels, the way you work with it, what customers are looking for, you know, from the business perspective, all those things are very important.
Our group was responsible for the actual project management from the standpoint of cost, functionality. We're responsible for the actual hardware design of the logic board, for the ASICs, as well as the system integration of the logic board. We were also responsible for the hardware associated with the display, the input devices, the battery subsystem, and so on.
Ergonomics is the science of common sense, but a lot of people developing products forget that.
Product design guy is always looking at the hardware guys. We kind of lean on each other. We even co-locate all the sub-assembly engineering teams to work in the same areas.
Every little surface, every little bit, every little corner we've defined and looked at and evaluated, from the latch, the way the latch feels, the way you open it up, the battery door, how it stays with the battery, how the battery slides out. Everything's been looked at very closely.
Should we make the unit thinner or thicker, or should we try to pull more weight out of the box and have a pointing device as a standalone option or through an ADB port? What should the battery capacity be? What is the software impacts of the battery technology that we're using? What about brightness control in terms of how much power are we going to allocate to the bulb so that we give enough brightness to the end user? Those types of decisions are an optimization of product marketing input, hardware design, as well as industrial design, talking through the various value engineering trade-offs of size, weight, cost, schedule, and so on.
What we usually do early on in the process is we'll have foam blocks made up to represent these components, and we essentially do a puzzle game, sort of playing with the engineering constraints balanced against the physical reality, which is how big it is, how it looks, how easy it is to deal with. It was clear to us that we didn't want to burden the user with an external input device, i.e. a mouse. The device we selected was a trackball. One option came up was at the right side of the product, which made some sense from a configuration point of view, but as we looked at it from the user perspective, we decided it wasn't appropriate to overlook the left-handers of the world once again. Then we looked at putting it in the front, and seemed like centered seemed to make sense. You know, a lot of times as a designer, when you approach something and you hit a wall, you say, let me look at this completely backwards, do something completely different. And something that came out of that made a lot of sense to us, and that was pushing the keyboard towards the back and moving hardware, and specifically the battery and the hard drive, forward. And what that ended up giving us was this very tight package that fit the trackball into the footprint we were looking for, and then place the keyboard here. And that also gives us this palm rest that allows you to sort of take your desk with you. At first, we all looked at it and thought, that seems pretty radical. We became very excited that we finally figured this thing out that had been bugging us for months.
Maybe not so much one huge eureka, but maybe more along the lines of a lot of small victories along the way. With all of our designs, what we try to do is not look at them as end products. We try to constantly use those designs and enhance them. And what we really want to look for is scalability for the future. We are road mapping the critical technologies that are important to portables. For instance, flat panel display technology, battery technology, mass storage devices, both floppy as well as rigid media as well as solid state capability. If you take a look at the overall hardware architecture of the microprocessor and the key I/O level of functionality, we have all of that road mapped for the next 3 to 4 years. We'll continue to ride the commodity items of batteries, of input devices, of displays and floppy drives and so on, We'll ride those commodity curves. If we push the industry and every single sub-assembly, we would never deliver product to the market. We have a very good relationship with Sony, and they understand how we do business. They had the infrastructure in place which we needed so that we could deliver the product concept and product ideas that we had developed here. We have partnered with them, and what we have done is we've brought to the table an overall design concept, both from the hardware, software, as well as the industrial design and product design piece. And what Sony has brought to the table is a complete design engineering team that has complemented our product ideas, as well as provided with the manufacturing capability and service capability as well to support us.
One thing that people notice right off that's different is the color. It's not our traditional Apple Platinum. We did that for a couple reasons. One, from a functional point of view, these products are handled a lot. They tend to show dirt, so we went to a darker value, obviously, to hide that, and so that they look fresh and new all the time. The darker colors did say to people, this is a richer thing. It's more of a personal item. In the desktop mode, some inclination on the product is real important, but in the laptop mode, you want it to remain flat. So we came up with this wheel idea. The reason it's round is it tells you that you have to rotate it to open it, and when you do, you'll notice as you rotate around, the little foot slides out and creates the angle necessary for the desktop use. When you're ready to go, you simply flip it back up into place, it retracts, and it's out of the way and ready to go. We've located the icons on the top. You don't get up and get around behind the product to look at the back. You look at the top of the product, you see, oh yeah, there's my icon, and it matches up with what's on the connector in the same orientations. We're doing some new things here that people haven't done before.
And when you think about what you could possibly do in the future with a portable notebook that has Macintosh functionality at the heart of it, it's just extremely exciting. And we're giving a customer or an individual the capability of a Macintosh II CI in something in 6.5 pounds.
Well, here we have it. This is the carrying case extended edition.
Thanks very much. You may want to know that we do have plenty of those extended edition carrying cases available in the company store. And in fact, Frank is looking at bundling those with his Quadras, so look for that in the store near you.
On Monday, we're finally going to get to announce these great new Powerbooks. It's also going to be great because I finally get to do a little bit of my laundry that's been piling up there. We have 3 products in our Powerbook family, the Powerbook 100, 140, and 170. It really spans the line between affordability and performance. It really gives our customers a choice to decide which product is most appropriate for their use and their budget. So let's go into a little bit of detail about the products.
Great, so looking at the processor with the Powerbook 100, it's a 68,000 at 16 megahertz. That's roughly the Classic 2 performance. The Powerbook 140 is an 030 at 16 megahertz. That's 2CX performance. And at the 2CI level, the Powerbook 170, 030, 25 megahertz with an FPU, the 882. In terms of RAM, all systems are expandable up to 8. The minimum configuration on the 100 and the 140 is 2 megabytes. And then on the 170, the minimum configuration is 4 megabytes. We'll be offering a 20 megabyte hard disk and a 40 megabyte hard disk in the line, as you can see up there. as well as Bruce mentioned, we're introducing a line of products. So that means with the floppy drive, for example, we can give the customers choices. So with the PowerBook 100, they have the choice of an external floppy drive, so they can take advantage of the smaller size and weight of the 100 and leave the floppy drive at their hotel room or back at their office. If they prefer an internal floppy drive, then they have the PowerBook 140 and 170 to choose from. Also, we have a full complement of ports. We have built-in SCSI and built-in networking, both of which distinguish these PowerBooks from any other notebook on the market today, as well as we have sound in on the PowerBook 140 and 170, sound out on all three products. We have an internal modem, 2400 baud, 9600 baud data modem. It's going to be bundled in the US on the PowerBook 170. So as you can see, a lot of the functionality that you associate with Macintosh desktops are now in these notebooks that is sub 7-pound machines. So a lot of achievements there.
And we got these machines down to the true notebook size. So the PowerBook 100, 8.5 by 11 by 1.8 inches thick, weighs 5.1 pounds. The PowerBook 140 and 170 share the same plastic, slightly larger, right around 6.8 pounds. So but to get to this small size, you can't just take the Macintosh Portable today and sort of stick it in the incredible shrinking machine and get it down to 6 or 7 pounds. It's really a lot of long, hard work across the entire system. So let's take a look at some of the components.
Okay, let's start with keyboards, and this is the keyboard for the original Macintosh Portable we introduced in 1989. And for the PowerBooks, Bruce?
Yeah, here's our new keyboard. As you can see, it's much thinner, saves about a ½ inch in height, and saves about 3/4 of a pound. So quite a bit of savings just in a dang keyboard.
RAM cards. This is a 1 megabyte RAM card that works with the Macintosh Portable.
And here's the RAM expansion card for the PowerBook. So that's going to be in 2 and 4 megabyte configurations on this card.
And this beefy guy is the rechargeable battery for the Macintosh Portable.
And here we have the new battery for the PowerBooks. It's a nice cartridge style. Gives you 2 to 3 hours of battery life, so improvements here too.
Okay, great. And Bruce, I'm kind of slow, but I'm noticing a trend here. Why do I always get all the big components?
That's because you're the big, strong guy here.
Thanks. Okay, so this is a 40 megabyte hard disk that went with the Macintosh Portable.
And right here, this is our new form factor, 2.5 inch hard disk. So this will be in 20 and 40 megabyte configurations.
And finally, the logic board of the Macintosh Portable.
And here we have it for the PowerBook 170. You can see it. You can see the difference. Again, 2 CI performance. So the next thing we're going to do is bring out the machines, right?
Sounds good to me.
So one of the things that customers always say is, can it fit in a briefcase? Thank you, Vanna.
Sure, Pat.
So here we go. Just open it up. Frank didn't lock it, did he?
No.
Here we go, and you can see it fits in sideways in the briefcase. This is a briefcase that I got as a graduation present from high school and have never had use for it till now. And then we have the PowerBook 140, and where's Wayne?
Back here, Bruce, just rolling. I got a personal laser writer, as you can see, and also as you can see on the overhead, the PowerBook 100 is 8.5 by 11, so there's some commonality here, and that's in the paper tray, which contains the PowerBook 100. So Frank, eat your heart out. So it's 8.5 by 11 by, what's the?
Must be about 250 sheets.
Something like that. Okay, great.
Don't try that at home. That's a specially modified printer, so it's not. Okay, so just to get it straight. So we got it down to the notebook size, sort of the leading edge in terms of size and weight. But we have to figure out, how do you do a pointing device? It's always fun to first look at the competition and see how they do it. So what we have here is sort of your sort of a standard DOS notebook computer with your, what do you call this? I think you call this sort of like the Microsoft jump rope.
Well, I've got some over here, Bruce. It's not quite as aerobic as what you have there, but still no less attractive. I don't know. What do you call this?
I
Bruce?
think like the Microsoft Wart.
The wart. Okay. So Bruce has a knack for product names. So we've got this wart here on the side. And what happens when you try to close the case, many people want to put these notebooks in their briefcase, is you'll be able to get all kinds of things in them, like leaded pencils and paper clips, small insects, I don't know, whatever in there, and it's going to cause reliability problems for your notebook. As well here, you've got this knob on the back that can break off as you put it in. So a lot of problems initially just as you look at it. Also, when we open it up, you'll notice this is a characteristic of all DOS notebooks, that the keyboard is pushed to the front. So as you use it, and you go ahead and type here, when you use it for any short period of time, your arm will naturally rest on either the tabletop or the laptop, depending on how you're working, and you're working in this kind of a position. And your tendons are in this position, your tendons in your wrist are tight. Increases the probability of tendinitis or carpal tunnel syndrome, as you may have heard. So some definite problems with both designs. What we've done, let's show you right now, is taken a very different approach. We knew we wanted a pointing device from the beginning, and so we integrated it into the design of the machine, and so now we have a complete design. You notice here that the keyboard, first of all, is pushed back, the trackball is in the center. That leaves room for some palm rests. I can set my palms here, go ahead and type on the keyboard, and you can notice my wrist is straight. It's what we call in a neutral position, which is a very good ergonomic position. I could then use with my finger still on the keyboard, I can use my thumb to control the trackball, and then with my other hand, I can control this button, which is the mouse button, or I can move down, use my index finger or middle finger, and then use the same button, or dual button control, use this button to control the mouse. So it's both for right-handed and left-handed people. As well as, since the keyboard is, it's a really hot design. As well, the keyboard is pushed back, so if I use it in my lap, unlike DOS computers where I would be crunched in here, I have plenty of room to type and work in a small area. So a lot of advantages there.
This is a design that many of you participated in the overall testing of this. So you helped evolve this design, and thank you very much for that. One of the other things that came out of the user testing was these little lifters here that provide some angle on the keyboard when you're using it on the desktop. So a very nice complete design. Now going on to displays. On the Powerbook 170, we have a backlit active matrix display. This display is the fastest, the brightest, the highest contrast, widest viewing angle display out there. So it's by far the premier display technology available on notebook computers. Then on the Powerbook 100 and 140, we use Super Twist displays. These are state-of-the-art displays, better than the best that are out there on any other notebooks. So we have a great story on the displays and in the ergonomics with the Powerbooks.
Great, so as you can see, we've got a great ergonomic story as well. We have advantages in networking. With built-in networking in all three products, built-in local talk, and file sharing, which is a standard feature of 7.0, which all these products will ship with 7.0. We can turn any one of the Powerbooks, I'll work with the Powerbook 100, we can turn that into a server and easily connect to the Macintosh desktop. So let's do that right now. Bruce, can you give me a hand?
Yeah, right here. Let's make sure.
Okay,
There's
no wires
no wires.
Okay. No tricks.
No tricks, no tricks.
You can try this at home. And I'll connect back in there. So I've just got a standard local talk cable. I've got the alias to the Powerbook 100, and I'll just double click on the alias and type my password in.
Does it work?
And here I am. All the contents, and this is quite easy to use, all the contents of my Powerbook 100 hard disk available to me on my desktop. We show this to customers, and they are extremely excited about this capability, given the fact that many of the notebooks are second machine users, are second machines, so they can bring the Powerbooks easily into their office and connect with their desktop. Customers, though, you may be surprised, but a number of our customers also own DOS machines. It's true, and we need to help them at least make some kind of productive use of these machines for things other than boat anchors. So we're trying to do that, and with the help of Fairlawn, which I have they have a PhoneNet Talk PC product. We have a PhoneNet Talk PC card in here, as well as the software. We can essentially connect our PowerBook 100, 140, or 170 to the DOS desktop, just as I showed you with the Mac. So a great connectivity, a great networking story with both the DOS desktop and our Mac desktop.
Great, but we know that sometimes our people using notebook computers are going to want to have access to those network services, but it's a portable, so they aren't going to be at their desktop, and they aren't going to have this network connection through the standard connections there. And so we have a brand new product. This is a really cool demo. Let's begin this. This is our new product, Apple Talk Remote Access. It's one of our new networking communication products out there. Can you hear it dialing? It's using the internal modem here. And so what we're doing is connecting this Macintosh through the standard telephone lines to another Macintosh that's over my desktop over in Valley Green 6 that has a modem attached. So it communicates that, establishes the connection, and once it answers and gets there, I have full access to the network, and it could do anything as if I was a local member of the network. This product was announced this last week at NetWorld along with AppleShare 3.0. So these products are really important for how these notebook users want to use their computers. In fact, it's a product that's available for $199, but it's so important for people who are using notebooks that we're bundling the software with all three PowerBooks. To show you that I'm not cheating here, let's go to the chooser, and you can see that there's really no networks there, and boom, they disappeared. So I have established a connection there. So I have access to all my zones, just as if I was local there. What else can I do? I could do things like go to the Apple directory, and here it is. It shows up here. This would be nice to do when I want to call Randy, our vice president, and say, thanks, Randy, for helping us create these new great products. Another great thing that you could do that I'm personally very happy to do is because I'm a pretty forgetful type of person sometimes. And when you're on the road, you want to have access to your hard disk. So what I'm running right now is using, I have Macintosh file sharing running on my desktop computer. And so in just a few seconds, what will appear is entire contents of my hard disk. So I could just go over there, bring back a file back and forth. A really important functionality. We show this to customers, and their jaws sort of drop. And they're going like, "Wow, I didn't know you could do that type of thing." So again, it'll show up in just a second. And there.
Bruce, how are you getting the video out onto the screen?
Yeah, thanks, Wayne. I'm using I'm using a Radius PowerView. So we've been working with lots of third parties and doing products for add-ons for the PowerBooks. And so one of these products is the Radius PowerView. There are a few other companies doing video out, RAM, and other accessories for the product. So it really helps us out here.
Great, so you can see we've got advantages in ergonomics, networking, communication, and based on the early feedback that we've received from the customers, there's going to be a whole heck of a lot of demand for these products for the foreseeable future. But we're leaving nothing to doubt because we're going to price these products very aggressively. You can see the pricing here. We've got a full range from the Macintosh PowerBook 100, the base configuration, the 220 at $22.99, all the way up to the 170, the 440 with the modem bundled at $45.99. So a good offering there, as well as a full complement of peripherals, fax modems, SCSI cables, RAM cards, batteries, etc.
At Apple in Fremont, California, people and machines work together to build the highest quality personal computers in the industry. This facility combines state-of-the-art equipment with a skilled workforce to achieve manufacturing excellence. First, certified suppliers deliver high-quality material to the Apple receiving dock. Then, logistics personnel remove material from its shipping containers, count it, and place it in a storage bin called a tote. This material receives a bar-coded serial number, which is entered into an MRP2 inventory system. Part number, vendor number, PO number, and quantity are all bar-coded on the shipping bill. Logistics personnel put enough material in each tote to adequately supply the assembly line. The raw material needed to build a Macintosh circuit board then moves toward the automated storage and retrieval system, known as the ASRS. This computer-controlled carousel system rotates to provide access to each tote. Totes move to the ASRS and are automatically inserted into the next available storage slot. The entire operation is monitored and controlled by Macintosh computers and trained personnel. When a request for material comes through, the ASRS selects the correct carousel and tote and delivers it to the pickup station. At this stage, the Automatic Guided Vehicle, or AGV, picks up the requested material. Then the AGV moves to the delivery location, following the black and white tiles on the floor. At the beginning of the assembly line, an operator loads a printed circuit board into a screen printer machine. The bare circuit board aligns to the assembly fixture using a video camera, which verifies known points on the board with a stored pattern in the machine. Then, solder, in the form of paste, presses onto the board through a brass stencil. This solder will later hold the electrical components in place. This screen printing operation is similar to creating silkscreen designs on fabric. Pick and place machines automatically inspect electrical components before placing them on the circuit board. A rotating tool head then places the parts on the top side of the board, where the solder paste was deposited. This process is known as surface mount technology. A skilled operator monitors the equipment to keep the machines filled with components and to ensure proper operation. Because of the various sizes and assembly requirements of the components, several different machines are used. Then, in an infrared oven, the solder paste melts or flows and binds the components to the top side of the board. This process is known as infrared reflow. The circuit board now flips over so that small components can be attached to the bottom side. The tween stations on this pick-and-place machine temporarily glue tiny components to the flip side of the board One station glues, the other places. These components will be soldered to the board later in the assembly process. The circuit board is subjected to infrared reflow to harden the glue, and then it flips back to the top side. The operator enters a bar-coded serial number which is used for real-time data collection and tracking. A mechanical shuttle moves the circuit board across walkways so that people have access to all areas of the manufacturing process. The assembly line is designed in a U shape to conserve space, and that requires that the circuit board be turned 90 degrees to continue on its journey. Robots pick up components which are tedious to insert by hand. These parts are picked up from a specially designed feeder mechanism. Small components like these speaker connectors automatically present themselves to the robot arm for insertion. If a component does not fit in the first few tries, the robot will pick up a new one and retry the insertion. All parts that have wire pins or tabs that go through the circuit board are clinched from underneath to hold them in place. This eyelet setter or rivet press secures any large connectors which are located at the edge of the board and which need extra strength. Some large components have to be hand-placed. A computer user may plug additional circuit cards, such as memory or a communication modem, into these larger connectors. The circuit board now contains all of its components. An operator makes a final visual check to be sure that the board is ready for soldering and, again, enters the bar-coded serial number into the online quality information system. A wave solder machine does the final soldering. Here, the bottom of the board is first coated with solder flux. This substance prepares the surface so that the solder will adhere correctly. Molten solder at 470 degrees contacts the component leads and electrical circuit connections on the bottom of the board. Notice, the hot solder just touches the wire leads. The circuit board assembly is now complete. An operator trims any long component wires and visually inspects the board. Another operator now tests each circuit board by putting it on a set of metal pins built into a tester. The tester exercises circuits and tells her whether the board is defective or good. Boards which pass the electrical test move into specially designed carts and go by truck to a nearby building on site. Boards that fail stay behind for more tests. Using sophisticated diagnostic equipment, technicians isolate defective components and mark them with a red arrow. At another station, a skilled technician repairs or replaces the defective parts. The circuit board is then retested and sent on to the final stages of the assembly process, which we will see next. Meanwhile, a recreation area and fitness center are conveniently located on site. Whether on the shop floor or on the basketball court, teamwork is a key element to manufacturing excellence at Apple. Building 1, the original Mac factory facility, continues to be the center of production for the final assembly and shipment of Macintosh systems. Design for Manufacturability, or DFM, makes the assembly of a Macintosh computer simple and efficient. This operator easily installs the speaker assembly and the data cables for the disk drives. The disk drive mounting bracket, along with the floppy drive, inserts into the case. The hard drive snaps into place and the drive power and data cables are attached. Next, the operator installs the power supply for the computer, and the system is powered up to prepare for the first phase of testing. During this first phase, test cards are temporarily installed to allow software to exercise all areas of the system. An operator monitors the testing and verifies that the system is running correctly. The test cards are removed and the top of the case is snapped on. Operators audit a select number of completed machines to monitor the quality of the assembly process. And then, the machines move into a run-in tower, where software exercises them continuously for 24 hours. When the Macintosh systems leave the run-in tower, they return to the assembly line on an elevator. Now the computers go through their final system tests. Any dirt, dust, or fingerprints are carefully wiped away. Then, a process monitoring Macintosh reads and verifies test results stored on a diskette. The system software loads automatically into the completed machine's hard disk. Next, an operator verifies the video image, and the completed system receives a permanent serial number and is bagged for shipment. If a system fails anywhere in the process, a conveyor takes it to a rework area. Here, a technician replaces any defective components and retests the system. Once the computers have passed all of their tests, operators begin the packaging process. Accessories such as a mouse, power cord, diskettes, and instruction booklets are packaged along with the Macintosh. A completed system and accessory kit automatically insert into a shipping box. Tape applicators seal the top and bottom, and the boxes move along a conveyor. Then, they collect together on a cardboard sheet to form a shipping pallet. A completed pallet is wrapped in plastic. The plastic wrapper protects the boxes and provides strength for the pallet. A forklift moves the completed pallet into a waiting truck. When the truck is fully loaded, it leaves the manufacturing facility and drives directly to Apple distribution centers. Working together, people and machines have created a complete Macintosh computer in about 36 hours.
time to get to work. Come on, guys, stand still.
Sorry.
Crank up the trapeze, Louie.
Sure thing, boss.
All the way to the top. It's gotta look dangerous.
Right. Hey, boss, that worm kid's still here for the audition.
What about the new lion tamer I asked for?
No way, boss. Not after what happened to the last one.
Nobody's got any guts in this lousy town.
But this kid's real keen, boss. He's been waiting all day.
Yeah, break my heart. So, kid, you want to be in the circus? Okay, show me what you can do. Sorry, you're just not what we're looking for. Hey, wait a minute. I got an idea. Go and grab the end of that rope. Go on, kid. Trust me. Try to roll with it when you land. Uh-huh. Nice try. But it's not really you. Okay, I got it this time. How do you feel about heights? Come on, kid, it's a cinch. No bones to break, right? Okay, Louie. Pull! Hey, kid! Speak to me, kid! Speak to me! Louie, get the dog! You got guts, kid. My circus can use a worm like you. Now tell me, ever thought about taming lions?
Apple's competitors have spent lots of time over the past few years deciding how a personal computer should look. Now, after years of engineering, it looks like they've reached a conclusion. They've decided it should look like a Macintosh. A lot of people in the press say that spells doom for Apple. But generally, these are the same people who predict the doom of Apple every year. The only thing that changes is the competitor. A year ago, it was Next. Before that, OS II. Before that, IBM's PC Junior. But even though our competitors may imitate the way Macintosh looks, they can't come close to the way it works. Today, we'll compare Microsoft Windows running on an IBM PS2 Model 70 with a Macintosh II CI to show you that Macintosh really is the best personal computer because it's the only personal computer with a unified architecture. And Apple is the only computer company that designs and builds all the fundamental parts of its system. As we'll see, that gives Macintosh big advantages in 4 key areas: ease of use, applications, networking, and future growth path. And these are advantages that Windows can't match, because where all the parts of the Macintosh, hardware, system software, peripherals, and interface, fit together as a unified whole, Windows has been added on top of DOS, which was never designed to support it in the first place. Once that point is clear, it's easy to help customers look past the surface of Windows and show them how deep the advantages of Macintosh really are. Of all the advantages that Macintosh offers, the one people know best is ease of use. That's what Windows is supposed to bring to the DOS-based world. But real ease of use can't be bolted on to an old-style PC. It has to be built in from the chips up, the way it's been built into the Macintosh from the very beginning, and the way every Macintosh user experiences it from the moment they open the Macintosh box. When it comes to setting up a Macintosh, for instance, all the user has to do is plug in a few cables. Software is already installed on the hard disk, so all the user does is plug in the power cord, hook up the monitor, attach the keyboard and mouse, hit the on button, and they're welcome to a happy Macintosh that's ready to run. But with a PC, plugging in the components is just the beginning, because users also have to format the hard disk, install the system software. Pretty complex task for somebody who's new to computers. After that, DOS will need to know what kind of components are hooked up to the system. And this is something the Macintosh understands automatically. Then, it's time to set up Windows. In the time it takes to complete these procedures and get one PS2 up and running, 30 Macintosh systems could be unpacked and configured. Or, people who haven't worked with computers before could spend that time taking a tour of the Macintosh to learn all the basic skills they need. That kind of helpful tutorial is something you won't find with DOS or with Windows. And it's as easy to expand a Macintosh system as it is to set it up in the first place. With a SCSI connector, a standard feature on every Macintosh sold today, we can connect peripherals like a hard disk, a CD-ROM drive, a scanner, in seconds just by plugging them in. And we can have all these devices hooked up to the Macintosh without using up any of its expansion slots. So we can add a second monitor or even a third and work with all of them at the same time. Now let's see what it takes to configure our IBM system with the same kind of peripherals. Since the Model 70 doesn't offer SCSI as a standard feature, we'll have to install individual interface cards for each peripheral, using up every one of our expansion slots. And since the operating system can't recognize hardware without our help, we'll have to run installation programs to configure the devices properly. We can't add any extra monitors to the IBM PC because we've used up all the slots. But even if we had the room, the extra monitors wouldn't do us any good because standard IBM PCs aren't designed to use more than one monitor at a time. We've seen that Macintosh has big advantages because of the way the hardware and software work together. Well, what if you ignore the hardware and just look at what the software can do? Some people say Windows matches the software features of Macintosh, but it just isn't so. The first thing to notice about Windows is that it has created two different panes, excuse the pun, Program Manager and File Manager. This combination of two applications is supposed to approximate the environment found in the Macintosh desktop. Program Manager is used to start your applications, and File Manager is used to move, copy, and delete files on the hard disk. But unfortunately, File Manager and Program Manager are both built on top of DOS, so they don't talk to each other. If we make a change in one, the other program may not notice. For instance, suppose we want to move our word processor from the directory called Windows in File Manager into the directory called Process. Moving the application files is easy enough. But then, when we go into Program Manager and double-click on the icon to launch the application, Windows gives us an error message. That's because Program Manager doesn't keep track of changes we made in File Manager. So when you click on the icon in Program Manager, it looks for the program in its old location. Now, if this sounds confusing to you, imagine what it's like for a computer novice. To correct the problem, we have to use the Properties menu in Program Manager and type in the new DOS path name for the program. A simple change that would have been handled automatically on Macintosh throws Windows users back into DOS. In fact, Windows has to work with almost all of the traditional DOS limitations because it's been built on top of DOS. So, where Macintosh gives you the freedom to call your files and folders whatever you like, Windows can only accept DOS file names with 8 characters or less, which forces you to create your own version of computer code. Where Macintosh lets you arrange your icons any way you want, File Manager icons are locked into the DOS directory tree. This prevents you from arranging them in the way that suits you best. And where the Macintosh can respond when you make a physical change to the system, like inserting a diskette, Windows isn't connected so closely to the hardware. So when you put a diskette into the IBM PC, it doesn't notice it until you tell the machine that the disk is there. Even worse, when we remove our first diskette, insert a new one, and try to look for a file, Windows displays the old disk directory on screen. This forces us to use a new command, refresh Windows, just to look at the files that are actually in the drive. Now, Macintosh does all of this automatically. But the unique combination of power and ease of use in Macintosh means more than convenience. It also translates into superior performance. Several independent studies have shown that Macintosh programs generally run faster than their counterparts in Windows. For instance, here's Microsoft's own PowerPoint program running on the Macintosh II CI and the IBM Model 70. Which computer would you rather use for a critical presentation? If your customers are still having a tough time telling the difference between Macintosh and Windows, introduce them to a few applications. Show them what a world of difference there really is. Because not only does Macintosh offer more applications than all other graphical environments combined, including Windows, Presentation Manager, New Wave, OSF's Motif, Sun's Open Look, and Next, it also provides consistency across all those applications. So once you learn your first Macintosh application, you'll be well on your way to learning them all.
Consistency on the Macintosh is really the reason why the Macintosh is so easy to use. In terms of running one application and then moving on to another application, moving between the application and the Finder. And the reason why applications are consistent is because we've built in the basic user interface functions into the ROM of the Macintosh. That's true from the original Macintosh introduced in 1984. Every Macintosh has these facilities built in. Every Macintosh comes with these facilities. And so every application on the Macintosh ever written uses these facilities in the same way. That means that applications look the same, they feel the same, They all operate in the same way. No other environment has provided this consistent level of functionality built into the computer, and so no set of applications on any other platform performs with this same kind of consistency.
Of course, Windows is supposed to introduce consistency to the DOS-based world, but let's see if that really happens. In fact, even with Microsoft's own applications, designed specifically for Windows, there are inconsistencies that could easily confuse users. For instance, selecting a word and pressing the backspace key executes a delete command in PowerPoint for Windows, but in Word for Windows, moves the cursor to the beginning of the word. And in Excel for Windows, it moves the cursor back one space, which poses the question: if Microsoft doesn't make Windows applications consistent, what chance is there that anybody else ever will? Conventional wisdom has long held that MS-DOS platforms offer the best connectivity, but reality indicates otherwise, because the unified design of the Macintosh incorporates connectivity features at every level of the architecture, with a network connector built into every Macintosh ever sold, with a native networking protocol, AppleTalk, incorporated into the Macintosh's operating system, with built-in tools that give users access to networking services and features with classic Macintosh simplicity, and with networking applications that connect Macintosh with all the most widely used networking environments, including TCP and OSI. But the important thing about networking in Macintosh is not just the connections we make, but the easy way we make those connections. For instance, in a small network, Macintosh users can share a laser printer simply by plugging their machines together. There's no other installation involved. In a larger business, Macintosh users can cut and paste information from other kinds of computers, even mainframes, mini-computers, in a completely Macintosh way. Now compare this networking strategy with the Model 70 at the high end of the IBM line, which ships without any networking capabilities.
You need to add an interface card to attach to the physical media your network is, the network you're sitting on. Once you've done that, you need to install the appropriate client utilities, and when you're ready to access your network resource, you need to know the network path to it. So you need to kind of give your computer directions how to navigate to these network resources you're trying to access.
With Macintosh, of course, none of these tasks is necessary, because the networking port is already built in, and because AppleTalk identifies new networking resources automatically. So when you plug in a new printer or file server, it appears in the Macintosh instantly. And since AppleTalk is compatible with both Ethernet and token ring cables, we can increase transmission speed without sacrificing simplicity. What's more, AppleTalk networks can communicate with networks from other vendors like IBM and Digital.
So we're committed to working with existing standards for the networking environment. We support different lower level protocols for accessing network resources, for connecting to certain media types, but we also provide enhancements on top of that. The way we view our Macintosh way of accessing network resources is a little bit different from other companies' view towards accessing network resources. We want network resources to operate in a consistent, intuitive manner. We want network data, or data out on the network, things people are trying to access, to operate in a very similar fashion to the way data on your local device will operate.
So far, we've seen some of the advantages that set Macintosh computers apart. Now let's look at what ties them all together. That's a track record of smooth, uninterrupted growth that includes the introduction of revolutionary new products like the laser writer, continuous enhancements like high-resolution color displays, and convenient multitasking. And since every Macintosh shares the same basic components and is based on the same unified design, they can all take advantage of these new innovations. Which means the investment users made in a Macintosh Plus 6 years ago is worth even more today. And since the most advanced Macintosh can still run applications created 6 years ago, the investment users made in information is safe as well. That kind of backward and forward compatibility simply isn't available in the DOS-based world, as the release of Windows 3.0 clearly shows. An independent research organization, IDC, has estimated that Windows 3 won't run on 75% of the DOS machines in use today. And of the machines that can run Windows, more than half, these are 802.86 machines with less than 2 megabytes of memory or limited graphics capabilities, will do so with very slow performance. That's a good point to drive home and a great way to highlight the cost of doing business with IBM PCs. Because even the newer IBM machines, like the Model 25 and the Model 30, can't run Windows 3. And the mid-range systems, the Model 3286 and the Model 50Z, may require additional memory or system enhancements to deal with Windows. And even if your hardware can run Windows, you'll still need to buy new applications or upgrades to take advantage of all of its new features. That's an upgrade investment that PC Week magazine estimates at $3,700 per machine. And when users have completed the upgrade to Windows, they'll have another upheaval to look forward to. This is because IBM and Microsoft have both stated that OS II, not Windows, is the operating system of the 90s, which faces today's PC users with a troubling dilemma. Should they commit to DOS, or Windows, or OS II? And if they guess wrong, what happens then? Another myth that sprang up in the wake of Windows 3 was that Windows can deliver all the benefits of the Macintosh on a less expensive DOS-based machine. Now this is odd, considering the price of this Macintosh II CI is actually lower than this comparably equipped IBM Model 70. Of course, some PC companies charge less for their machines than IBM. But the cost savings of a PC clone also come with some risk, that the manufacturer will go out of business, that product support will be spotty, that there may be incompatibility or product quality problems. But more important, the cost of buying a computer is not the same as the cost of owning it. When you factor in training time and other ownership expenses, independent researchers like the Gartner Group say Macintosh is thousands of dollars less expensive to own than a PC running Windows. Macintosh and the PC have about the same administration cost, but Macintosh has lower support costs, lower operations costs, which include the time users spend trying to learn new aspects of their applications as they work. For a business, these savings go straight to the bottom line in improved productivity. For an individual user, they save something even more important than money, your time. Because with Macintosh, you can spend more time getting your work done instead of figuring out how to do it. Whenever you're comparing Macintosh against PCs, it's important to remember that Apple designed Macintosh as a complete system, not a patchwork of separate components that were retrofitted together. Because Apple understands the importance of the graphical interface, every Macintosh comes bundled with a mouse and operating system. Whereas with most DOS machines, the interface and the mouse are add-ons. You have to buy them separately. Because Apple understands how important it is to share information, most Macintosh computers sold today come with SuperDrive, a disk drive that can read and write to Macintosh, DOS, OS II, even Apple II disk. And with third-party products like SoftPC, Macintosh can run DOS, even Windows applications, so you can preserve your investment in software and information. Because Apple has foreseen the importance of sound in computing, every Macintosh comes with sound hardware and software built in. While the IBM PC can't do much more than beep, a Macintosh can do all this.
I know you're going to like the curve fit on this last set of data. It's just what we need to take to Dean Whitlow.
That gives Macintosh users a jump on the future in areas like voicemail and education.
Elizabeth was a beautiful princess. She lived in a castle and had...
Because Apple understands the future of color in computing, Macintosh can display up to 16.8 million colors on the screen without special software. Compare this with the majority of DOS machines, which still work with the VGA standard, which offers only 16 colors. Because Apple understands how important it is to put people in control of the computing environment, we developed HyperCard, the first application to give users real programming power. And we ship it free with every Macintosh, as opposed to the Windows environment, which can only offer Toolbook, a slower and more complex program that comes with a suggested price of $395, and according to reviewers, requires a faster 386 processor to perform acceptably.
You need to have a 25 megahertz 386 machine. You got to have a lot of RAM. You got to have a big hard disk. It's going to cost you a fair amount of money to get into this thing to make a usable configuration of your PC. Now that's true for Windows also, so this shouldn't be a surprise. We think Toolbook, because of its speed issues, because of the modality interface, because of some of its limited capabilities for doing report generation and printing, is going to tend to inhibit people after the first blush. Like a lot of products, Toolbook is going to have a honeymoon. It's clearly the best thing that's been seen in the DOS world for a long time. On the other hand, we think after the honeymoon's over, people are going to wake up and realize that Apple really does have a superior solution in many ways because Apple has a superior philosophy of design for its products.
As you can see, when you put Macintosh and Windows side by side, it doesn't take long to show the advantages of the Macintosh unified architecture. Greater ease of use, more consistent applications, built-in networking, and a smooth, uninterrupted growth path. The real question is, what do these advantages mean? It's simple. More satisfied customers. That's what an independent research organization, Diagnostic Research Incorporated, found out when they interviewed MIS managers and individuals who have used Macintosh, DOS, and Windows. The MIS managers rated Macintosh higher both in user productivity and in ease of use, while users rated Macintosh higher for ease of use and as a source of satisfaction in their jobs. When asked how satisfied they were with their computers overall, managers and users both gave Macintosh the highest rating. When it came time to recommend purchase of a particular system, both MIS managers and users did what came naturally. They gave Macintosh the strongest recommendation. That may be the most powerful Apple advantage of all, because when it comes to demonstrating the real power of Macintosh, satisfied customers are the most persuasive evidence we have.
We need to have a healthy attitude to respect even these insignificant problems with ESD. Once you are aware that they are occurring and that they can lead to worse problems or to frustrating situations, and you take a step to rectify it before you have hard failures where it's identified as a failure, you're doing a very, very good thing in your life. And I think part of the problem is there's not enough knowledge about what simple, easy steps I can take that really do matter and do work. It's a little bit of a subject that's just secondary enough, just low enough priority that it doesn't quite get, it's not visible to everyone.
Hi, I'm David Cram of Apple Service. I know you'll be thrilled to hear that the computer service industry has a problem that many of us have never really faced before. Sparks. The kind you get on a dry day when you touch a doorknob, only much, much smaller. So small you can't see them, you can't feel them. They never used to bother us much. Integrated circuits were pretty coarse 10 years ago, but now we have circuits so small and so fragile that very low voltages can make chips like these stop working. Or worse, cause them to look like they're working but do weird and unreliable things. And it's getting worse. Just about every computer product made today has chips in it that can be damaged by the charge that's just resting in a necktie or a synthetic sweater. We're talking about ESD, electrostatic discharge. Here's what happens. When some dry non-conductors separate, they each take an opposite charge. If there's a conductor nearby, the non-conductor will induce a charge on the conductor, and the conductor discharges it when it gets close to another conductor. And that discharge is what causes the damage. When you walk across a carpet, your shoes separate from the carpet, creating a charge on them. And the charge on your shoes creates a charge on your feet by induction. Now your sweat layer makes you a conductor all over, and the charge clings to the surface of your body until you touch another conductor like a doorknob or another person or an IC chip. Then it discharges in the form of a miniature lightning bolt. If you can feel it, it was at least 3,000 volts. 10 years ago, these things had traces big enough to tolerate a 3,000 volt hit and still work. But some of the traces we're using now are so thin they can be damaged by as little as 30 volts. It'd have to be 100 times stronger for you to even feel it. What do you have to do to generate 30 volts? I'll raise my arm. That's about 225 volts. As you can see, it doesn't take much. There are two kinds of problems. One is the field created by certain non-conductors, such as plastics. The other problem is discharge from one conductor to another. How do we know about all this? I can't touch a working chip and then take it apart and show you the damage. We'd have to use an electron scanning microscope that magnifies several thousand times. It's an expensive process and not something we'd do casually. But if you take the top off the chip and look for damage, and if it looks like this, or this, you know it was caused by a spark. Believe me, if you need proof, we've got tons of hard evidence and thousands of photographs. Actually, we believe in a lot of things we can't see. Germs, radio waves, radioactivity, for just a few examples. 150 years ago, the medical profession had never heard of germs, and it took a long time to convince surgeons that they have to scrub up before cutting into someone and not just wash up afterward. Another example is radioactivity. We believe in it not because we can feel it, but because we know its effects can be horrible. Now, it's not so important for you to understand exactly what happens inside the chip when it gets zapped by an electrostatic charge. It is important to accept the fact that something happens, something bad, to the boards that you care about. This is a machine built by 3M to demonstrate the reality of ESD damage. Here we have a MOSFET transistor, but what we're going to see done to it could be done to a CMOS chip just as easily. First, we're going to test one. And if it's good, she can set this to 10, and this won't go above 325. So that's good. Now we'll check it for leakage. And as the transistor warms up, that should come down to 0. The tension mounts. Okay, we got a good one. Now I'm just going to charge myself and touch it. And we got a dead short. Let's try it with a new one. Okay, check it for... This is just an overhead transparency foil. I'm not actually going to touch it, but we're representing the kind of problem caused by bringing charged non-conductors close to a chip. Okay. And also this time we're going to put it on a little board. Just put it on that. Okay, now I want to wave this over the top without touching it. I'll wave it under the bottom. Okay, now check it again. Okay, that part's still good. Check it for leaks. Uh-oh, it has a short. And I didn't touch the transistor. That transistor passed a functional test, but it leaks. It's going to fail in the field. And we know all too well when a damaged chip finds its way into a computer, it can have aggravating consequences. How can we stress this? 100 years ago, the medical profession didn't really believe in bacteria. Now they take elaborate precautions to keep their working environment sterile. We're just beginning to realize that we have to be just as meticulous about static if we want our patients, the chips, to survive and function properly. Now, you might be saying to yourself, hey, wait a minute. I've been handling boards for years without protection, and I sure haven't experienced the kind of failures you're talking about. Well, there are two reasons for that. One is that as crowded as these integrated circuits are, there are still a lot of places where a zap won't hurt anything. And the other reason is that most of the time, sparks only wound. They don't kill. So if you wound one, and if it fails outright in a month or two, well, you've gotten away with murder. It's question time. Take a look at the following and tell me if the chip on the bench is going to be all right. The cup is a non-conductor, and when he separated it from another non-conductor, it picked up a charge. He placed the charged non-conductor near the chip, and inside the chip are conductors. Let's look at a slow-motion representation of what happens. As the field surrounding the cup envelops the chip, it causes voltage changes in the traces. And if the voltage reaches a level high enough to jump, it burns a hole between the traces. The spark's heat vaporizes the metal, which then condenses on the sides of the hole. If it creates a direct short, we're lucky. Usually it doesn't, and we have a degraded circuit waiting to fail in the field. We can get rid of a charge on a conductor by touching another conductor, but the cup is a non-conductor. How do we get rid of a charge on a cup? The only way a charged non-conductor can get rid of its charge is for the ions, positive or negative, that make up the charge to unite with ions of opposite charge. The air has ions floating free, and gradually the cup will find enough to go back to neutral. But that can take quite a while. Hours, days. If you want to hurry the process along, an ionizer generates both positive and negative ions, and as they flow around the object, it takes what it needs. But even an ionizer can't neutralize the charge quickly enough to prevent damage, which happens in the first few millionths of a second. So what can we do? Well, the basic rules are simple. If the device is not being worked on, it should be in a shielded bag. If the device is not in a shielded bag, don't touch it unless you're grounded with a wrist strap or a heel strap. And don't let ordinary plastics or synthetic clothing get close to it. Let me show you something. This is a gadget that spits out positive and negative ions. I'll just prove it to you with my static meter here. Positive and negative. Now zero the meter. This is a new bag. Now put the meter inside. Turn it on. Zero it. And then I will fire the gun at it, and there isn't a wiggle. Now this bag has a little scuff in it, has a lot of little pinholes, and again I will zero the meter. As you can see, this is allowing 200 or 300 volts to seep through the bag. When we say put it in a shielded bag, we mean a good one, not one with a lot of holes or a lot of scuff marks on it. If you see a worn bag, test it. Don't risk a $100 board to save a 60-cent bag that's already lived a rich, full life. While we're at it, let's see what happens when you put it inside a bag that's anti-static but unshielded. This is a typical anti-static bag, but it's unshielded. Put the meter in. Zero the meter. Oop, better set that on high. Zero the meter. And as you can see, it's allowing 4,000, 5,000 volts to seep through. This bag won't cause sparks, but it won't protect from a field that's placed near the chip. By the way, we used to think that once the chip was mounted on the board, it was no longer susceptible to ESD damage. Not so. In fact, the possibility of damage actually increases because the traces and leads on the board act as antennae. A proper workstation will have a conductive mat grounded to earth ground, to which the worker attaches a wrist strap cable. When we say ground, we mean real earth ground. The ground wire in a modern building will probably be all right, but you can check it with a ground checker. The wrist straps have to touch the skin, or they don't do any good. If the worker can't wear a wrist strap because it hampers movement, he can wear heel straps, which go from the moist inside of his shoe to ground by passing under the heel. Of course, he must be standing on a floor pad that's both conductive and grounded. By the way, I've had techs tell me that you don't have to worry about grounding unless you have carpeted floors. That's just not true. It doesn't matter what you have on the floors. If you're not grounded, you can't be sure you're ESD safe. The tools used at the bench, like soldering irons, have to be grounded. And devices like solder suckers must be made of conductive plastic. These old blue ones can generate several thousand volts on a dry day. Be careful of heat guns. Some can generate over 10,000 volts directly on your work. And don't use toothbrushes to clean your work. Brushes should be natural bristles, not plastic. And storage bins should be made of conductive plastic. A technician working in the field has to set up a temporary workstation, tie into a building ground, and wear a wrist strap. It isn't enough just to touch the power supply because every move he makes will generate new charges. And of course, he should never set parts on the carpet or near plastics. Okay, let's see if you can answer some more questions. Watch this scene and see if you can spot anything wrong.
Hi, Dave.
Can I borrow this tool for a second?
Sure, go ahead.
Thanks.
Did you see anything wrong? Let's look again. The tech walks up wearing a synthetic jacket,
Hi, Dave.
Can I borrow this
probably
tool for a
loaded
second?
with static. He doesn't touch a thing, but when he reaches across to get the tool, his jacket almost touches the work on the bench. And that could be enough to hurt the board. Try this one. Is anything wrong? Take a look. The saleswoman is bristling with static. She opens the box to see if it's the right part, and when she does, she risks zapping it. She should put on a wrist strap before opening it. Incidentally, if the part comes in a box like this, be sure to store it and ship it in the same box. Here's another one. What's the problem? He has anti-static carpet on the bench, and he's just sprayed it. Now, the carpet won't spark to the board he's working on, but it isn't grounded, and the technician isn't grounded either. As soon as he generates enough static, it'll discharge to the nearest conductor, probably the board. I'm sorry to say, all those lovely carpeted benches really have to go. Another problem is that the board was left out in the open. Air is a major generator of static. Think about that the next time you see lightning. And the board should not be bathed in open circulating air any longer than necessary. When you're through working on a board, or when you're through for the day, put the board you're working on in a shielded bag. Try another one. Did you see the problem? She's grounded. All looks good. But what's this? Non-conductive plastic bins? If they've been sitting here, they're probably neutral, but once a bin has been slid out, it can have a charge, and the parts in it could be damaged. Another problem is her hair. Her body is grounded by the wrist strap, but her hair is a non-conductor. Depending on how hard and how recently she brushed it, her hair is easily capable of damaging the piece she's working on. Try this one.
Gina, this is our service
Uh-oh,
area.
here comes the boss with a visitor.
And I'd like to show you some of the equipment that we have. This is one of our logic boards right here. And as you can see, it's very complex with the memory and the microprocessors on it. Get a good feel for it, okay? We'll just place that down there. Let me take you over here and show you over here, okay?
It's easy to see what was wrong, but not so easy to know what to do.
Very complex.
The boss was ungrounded, as was the visitor. Neither had any business touching the board, but what's the technician supposed to do? That's a tough one. He sure can't embarrass the boss in front of a visitor. He could wait until the boss is gone and then trash the board. After all, you have to assume that any board handled like that is at least wounded and in ways you may not be able to discover before it gets back to the customer. Realistically, you can't discard a board that passes functional tests, but at least the board should be retested and burned in again. Now, let's take a quick look at some of the things we'll have to do to protect our boards from ESD damage. Technicians will have to adapt to grounded workstations and get used to wearing straps. The salespeople, the clerks, even the boss will have to resist any temptation to touch a board unless they've grounded themselves first. On-site service technicians will have to take the same precautions the mainframe people take, or risk being tossed out by the informed customer. And since some computers have open tops and peripheral cards, even end users will have to be taught proper grounding techniques at the time of sale. Grounding to the chassis isn't as good as grounding to a good earth ground, but it's a lot better than not grounding at all. Just be sure the unit is plugged in and turned off. End users will need to know how to handle sensitive parts. In fact, we want to educate the end user to look for proper grounding procedures when he selects a service center.
Hi, Hi, here's the board that I called you about.
Thank you very much.
Thank you.
Because when the customer brings in a card for repair, he should know that if it's not protected, he himself may have damaged it.
We'll do what we can.
We all have to observe 3 simple rules. If you're not working on it, shield it, either in a bag or inside a computer system. If it's not shielded, don't touch it unless you're grounded. And if it's not shielded, don't let non-conductive plastics get close to it. We want the personal computer to be as reliable as the toaster. But if it does come in for repair, we want to be sure it goes home fixed. It's up to you.
You know, even from personal experience, I've had a lot of my own equipment, and I'm not working day in day out passing a lot of equipment through my hands. It's what I own and use. I've had a lot of it fail for ESD reasons. I mean, one of the key architecture features of the Apple II that was a huge plus for the whole industry getting kicked off actually came about because of an accidental ESD experience.
Tell us about it.
Sure. The first design of the Apple II said the cheapest memory chips are 1 megahertz. A TV line scans across for 40 microseconds of video and 25 microseconds of blanking. So I gave the video circuits, in the first Apple II design, gave the video circuits 40 microseconds in a row, 40 cycles of RAM. And then I gave the microprocessor 25. And I thought holding the microprocessor off for 40 microseconds was plenty safe. All the specs assured it. The engineers on the phone assured me that it could go for 2 milliseconds. But the Apple IIs I was demonstrating, they would fail. All of a sudden, the processor would go bad. The 6502 would go bad. So I'd plug a new one in, and it would work fine. And I had this dead 6502, but for some reason, it still worked in an Apple I. It was a very weak effect that caused it not to work in my Apple II design, but it did work in the Apple I design. Well, it forced me to figure out that the electrostatic discharge, one time I actually noticed a spark, and right when it went bad, and I knew that that's what led me on to it really was some sort of electrostatic discharge was not destroying the chip, but it was ruining a parameter that wasn't clearly specified in any data sheets. And I finally determined that, okay, you cannot hold this processor off for 40 microseconds. You can when it's brand new, but you cannot a week later. Every single one I used, you could not a week later. And that led me to search for the fact that now the 2 megahertz RAMs were inexpensive, and by going 2 megahertz, we could have video processor, video processor, video processor. It's a very famous characteristic of the Apple II that helped make a lot of its architecture work so well and give it such great performance. And it came about because I was trying to solve an ESD-related problem. ESD protection, when it's a disastrous failure, it's spotted instantly. You know, we can all put a weight on that. One of the worst things about ESD failures is that sometimes they're partial. They are intermittent. They cause a computer that will occasionally run for a few hours and then crash, but it can't be traced. You try to run all the tests on it, everything seems to run fine. These intermittent problems are the worst ones. They're the hardest ones for technicians or normal people to deal with. You can go for several months before usually the problem gets worse, is the only way you ever do get it rectified. If you have a sloppiness about your whole approach, eventually it's going to lead to some of the more disastrous problems, particularly later in your own career.